Terminating more than one ground conductor under the same lug is permissible under certain conditions, but it's crucial to adhere to relevant electrical codes and best practices to ensure safety and proper functionality. Firstly, the lug itself must be specifically listed and labeled for multiple conductors. The manufacturer's markings on the lug will indicate the number and size range of conductors that can be safely and reliably terminated. Using a lug not rated for multiple conductors can lead to loose connections, overheating, and potentially dangerous ground faults. Secondly, the conductors must be within the approved size range for the lug. The lug's listing will specify the minimum and maximum conductor sizes it can accommodate. Exceeding these limits can compromise the mechanical and electrical integrity of the connection. Thirdly, when terminating multiple conductors, ensure that each conductor is properly stripped and inserted fully into the lug barrel. The insulation should be stripped back to the appropriate length to allow for a secure connection without exposing excessive bare conductor. Fourthly, the lug must be tightened to the manufacturer's specified torque value. Using a torque wrench is essential to achieve the correct clamping force. Over-tightening can damage the lug or conductors, while under-tightening can result in a loose connection. Fifthly, the grounding conductors must be properly identified. Typically, grounding conductors are green or bare. Clear identification is crucial for safety and troubleshooting purposes. Sixthly, the enclosure or equipment where the lug is installed must be properly grounded. The lug must be securely connected to a grounding electrode conductor or a grounding busbar that is connected to the building's grounding system. Seventhly, when multiple grounding conductors are terminated under a single lug, consider the overall opacity requirements of the grounding system. The size of the grounding conductors and the lug must be adequate to handle the potential fault current. Eighthly, consult the National Electrical Code, or NEC, for specific requirements related to grounding and bonding. The NEC provides detailed guidelines on conductor sizing, lug selection, and installation practices. Ninthly, always follow the manufacturer's instructions for the lug and the associated equipment. The manufacturer's instructions will provide specific guidance on conductor preparation, termination procedures, and torque requirement. Tenthly, regularly inspect grounding connections to ensure they are tight and free from corrosion. Loose or corroded connections can compromise the effectiveness of the grounding system. For example, NEC Section 250.8 permits the use of pressure connectors, terminal bars, and splicing devices listed for the purpose with multiple conductors. These connectors will be marked with the quantity and range of conductor sizes that can be installed. The proper installation and maintenance of grounding connections is critical for electrical safety. Grounding provides a low impedance path for fault current to return to the source, which helps to trip over current protection devices like circuit breakers and fuses, thereby preventing electrical shock and minimizing damage to equipment. In addition to the NEC, other relevant standards and regulations may apply depending on the specific application and location. Consult with a qualified electrician or electrical engineer to ensure compliance with all applicable requirements. Moreover, when working with electrical systems, always prioritize safety. De-energize circuits before working on them whenever possible, and use appropriate personal protective equipment, or PPE, such as insulated gloves and safety glasses. Verify that circuits are de-energized using our reliable voltage tester. Furthermore, proper grounding and bonding are essential for electromagnetic compatibility, or EMC. Grounding helps to minimize electrical noise and interference, which can disrupt the operation of sensitive electronic equipment. A well-designed grounding system can improve the reliability and performance of electronic systems. Different types of grounding lugs are available, including compression lugs, mechanical lugs, and set screw lugs. Each type of lug has its own advantages and disadvantages, and the selection of the appropriate lug depends on the specific application requirements. Compression lugs provide a reliable and gas-tight connection when properly installed with the correct crimping tool. Mechanical lugs are easier to install and do not require special tools, but they may not provide as reliable a connection as compression lugs. Set screw lugs are commonly used for terminating small gauge wires, but they are not suitable for high current applications. The selection of the grounding conductor material is also important. Copper conductors are generally preferred for grounding due to their excellent conductivity and corrosion resistance. Aluminum conductors can also be used, but they must be properly terminated to prevent corrosion. Bimetallic connectors are used to connect copper and aluminum conductors to prevent galvanic corrosion. In summary, terminating multiple grounding conductors under a single lug is permitted, provided that the lug is listed and labeled for the purpose, the conductors are within the approved size range, and the connection is properly installed and maintained. Always consult with a qualified electrician or electrical engineer to ensure compliance with all applicable codes and standards. Remember that electrical work can be dangerous, and safety should always be the top priority. Understanding the principles of grounding and bonding is crucial for ensuring the safety and reliability of electrical systems. Grounding systems protect people from electric shock, prevent equipment damage, and minimize electrical noise. Proper grounding practices are essential for all electrical installations, from residential wiring to industrial power systems. In addition to the physical connections, the design of the grounding system is also critical. The grounding system should be designed to provide a low impedance path for fault current to return to the source. This can be achieved by using adequately sized grounding conductors and minimizing the length of the grounding path. The grounding system should also be designed to minimize ground loops, which can create electrical noise and interference. Ground loops occur when there are multiple paths for ground current to flow, creating a circulating current that can interfere with sensitive electronic equipment. To minimize ground loops, use a single-point grounding system where all grounding conductors are connected to a common grounding point. The location of the grounding electrode is also important. The grounding electrode should be located as close as possible to the service entrance to minimize the length of the grounding conductor. The grounding electrode should be installed in an area with good soil conductivity to ensure a low impedance connection to ground. The NEC specifies the types of grounding electrodes that are permitted, including ground rods, metal underground water pipes, and concrete encased electrodes. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. Grounding connections should be checked for tightness and corrosion, and the resistance of the grounding system should be measured to verify that it is within acceptable limits. Ground fault circuit interrupters, or GFCIs, are an important safety device that can protect people from electric shock. GFCIs monitor the current flowing in the circuit and trip the circuit if there is a ground fault, which is a leakage of current to ground. GFCIs are required in many areas, such as bathrooms, kitchens, and outdoor locations, where there is a high risk of electric shock. Arc fault circuit interrupters, or RFCIs, are another important safety device that can prevent electrical fires. RFCIs detect arc faults, which are dangerous electrical arcs that can occur in damaged or worn wiring. RFCIs strip the circuit if an arc fault is detected, preventing the arc from igniting nearby combustible materials. RFCIs are required in many areas, such as bedrooms and living rooms, where there is a high risk of electrical fires. Surge protective devices, or SPDs, protect electronic equipment from voltage surges, which are sudden increases in voltage that can damage sensitive electronic components. SPD divert the surge current to ground, preventing it from reaching the equipment. SPD are recommended for all electronic equipment, especially computers, televisions, and other sensitive devices. In addition to grounding, bonding is another important aspect of electrical safety. Bonding is the practice of connecting all metal parts of an electrical system together to create a low impedance path for fault current to flow. Bonding helps to equalize the voltage between different metal parts, reducing the risk of electric shock. Bonding conductors should be sized according to the NEC and should be securely connected to all metal parts. Proper grounding and bonding are essential for the safety and reliability of electrical systems. By following the guidelines in the NEC and other relevant standards, you can ensure that your electrical system is properly grounded and bonded, protecting people from electric shock and preventing equipment damage. Electrical safety is a shared responsibility. Everyone who works with electricity should be properly trained and should follow safe work practices. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Remember that electricity can be dangerous, and safety should always be the top priority.